All right, so we are going to go ahead and get started because I want to make sure we can get through everything today. You may have gotten an alert from D2L. Earlier, I uploaded 2 videos because I have a feeling we're not going to be able to get to some of the stuff at the very end of section 3.3, but I did want to be able to show it to you and talk about it a little bit. So I went ahead and made a couple videos for that, for those topics. So let me switch over to screen sharing so you can see what I'm talking about. Okay, so here is our D2L. Also, before I show you those videos, let me just remind you, I forgot to mention this yesterday. I posted it like right before, it was either right before or right after our session, so you may not have seen it. But this is for people that are interested in joining a study group for our class. So I set you up a separate group in Microsoft Teams, and this is how you can join. So I just put the steps for how to join, and it's use a code, and the code is right here, FTXU7GH, and that'll join you, or that'll, go ahead and add you into that study group. All right, so Rebecca, yes, I did get your message. I haven't responded to it yet, but I will after this session. Let me see. I'm looking at your problem right here. Y'all can see, y'all have my screen sharing. Find the upper class limit of the second class. Oh yeah, I remember we talked about this the day that someone brought this up that day that we were going through the frequency distribution. I think that for the second class, they want the upper class limit to be 80. So they would say like the lower class limit is 70, and then upper class limit 75, and then lower class limit for the second class would be 75 and then 80. I think that's what they want. But if anyone else has had this problem, you can share in the chat what you did. Let's see if I can go back to our group. I can't remember who said that. All right, but I did want to show you where I put those videos. So I just clicked on content, and then I'm going here to unit 2. And then if you scroll down to additional resources, I uploaded 2 videos. So I've got one about using the interquartile range to identify outliers, and then one where I show you how to calculate and compare standard scores, which I call Z-scores on the practice test. I didn't even realize that I called them that. But on the practice quiz, I called them Z-scores. So just know standard scores is the same thing as Z-scores. All right, so that's where you can find those videos if we're not able to get to those topics at the end of today's live session. 80 worked. Okay, you're welcome. All right, so let's get started. I didn't mention due dates, but the Unit 2 quiz is due on the 16th of September that night, and that's when the homework's due as well, and the practice quiz is due that same time. So Wednesday, the 16th, by 11:59 p.m., so right before midnight. All right, so we are finishing up section 3.2, which was measures of dispersion. The last 2 things we need to talk about are the empirical rule and also Chebyshev's theorem. So we're going to start off with empirical rule, which is maybe a little bit easier. The empirical rule only works for bell-shaped distributions. So what that means is distributions that look like this. Right, so the shape of the distribution has to look like this. Whoops, my line got off there. Try again. Yeah, so the distribution has to look like that. This is also called a normal distribution, so bell-shaped, also known as normal. All right, so this is the empirical rule for bell-shaped distributions. The empirical rule says that if you have a bell-shaped distribution, then approximately 68% of your data values should lie within one standard deviation of the mean. Approximately 95% of the data values should lie within 2 standard deviations of the mean, and 99.7, so almost all of the data values should lie within 3 standard deviations of the mean. So let me draw you a picture to show you what this means. All right, so here's I'm going to try to draw a bigger bell-shaped distribution. Let me try again. So here's our bell-shaped curve. It's much harder to do on this little writing tablet. All right, so imagine that one of the things that's normally bell-shaped distribution is IQ scores. So let's imagine that this bell curve represents the IQ scores. Okay, so what this means is that most people are going to have IQ around in the middle here, and the average IQ I think is about 100. All right, so the mean is 100. And the standard deviation of IQ scores is 15. All right, so I could go ahead and write out all of my standard deviations. So this would be 1 standard deviation below, 1 standard deviation above. So 100 plus 15 would be 115. If I was going below the mean, that would be 100 minus 15, which would be 85. If I went 1 standard deviation further, 85 minus 15 would be 60. And then 1 standard deviation further would be 45. And then if I go in the other direction, 1 more standard deviation, 115 plus 15 would be 130. And then 1 more standard deviation would be 145. All right, so what this means is that most people are going to have you can see, remember, when it's bell-shaped, that means the mean, median, and mode, they're all in the middle here. So most people are going to have an IQ of around 100. And then you're going to have some people, notice how the curve is much shorter. You're going to have a few people that have a really high IQ, like 145. And then you're going to have a few people that have a very low IQ, like 45. And then some people will fall in the middle here. But you can see that most people, the highest peak is here at 100. That's what most people's IQ is going to be. So let's say that we took a poll of our class and we made everyone in the class take an IQ test. What the empirical rule says is that approximately 68% of the class would have an IQ within 1 standard deviation of the mean. All right, so that means, let me change my color here. That means that about 68% of people in the class would have an IQ between 85 and 115. So this is 68% of the class. I'm just going to shade this part in. So this is 68% of the class would be in this area, this shaded area. The next part of the empirical rule says that 95% of the class would have an IQ between 60 and 130. All right, so let's change colors again. So they're saying that 95% of the class would lie in this range. All right, and the green is, again, 95%. And then the last part of the empirical rule says that approximately 99.7% of the class would have an IQ between 45 and 145. So that leaves just a tiny, tiny percentage that is not covered between 45 and 145. So hopefully that makes sense to what the empirical rule can do for us. So it can allow us to figure out what percentage of our data values lie between certain values. And the way that I do this, if I'm using the empirical rule on a problem, is I will start by drawing out this little distribution. So I'll start by drawing my bell-shaped curve. I'll label the middle as the mean. We learned that yesterday. we learned that for a bell-shaped curve, the mean lies in the middle. So you go ahead and label the mean, and then you can label 1, 2, 3 standard deviations to the right, and then 1, 2, 3 standard deviations to the left. And I just wanted to show you also, if we were just labeling this with our symbols, we could put the mean is in the middle, so that's mu, and then this would be 1 standard deviation, so 1 times sigma, and then 2 standard deviations, so 2 times sigma. 3 standard deviations would be 3 times sigma. On the other side, when we're going below the mean, this would be -1 sigma, because that's 1 standard deviation below the mean, so negative means below. This would be 2 standard deviations below the mean, and then 3 standard deviations below the mean. So that's what the symbols would look like for our standard deviations above and below the mean. And just to remind you, this little sigma, it's kind of like a, I've seen some people draw it like an O with just like a tail on it. I draw it like this, like a little kind of backwards circle, sort of, and then curl the tail at the top. So that's a sigma. And again, sigma represents this population standard deviation. So population standard deviation. All right, so let's look at an example where we are using the empirical rule. Some of the examples using the empirical rule are going to be pretty easy, and then some of them we'll have to sort of break down, and it won't be enough just to know that 95% is within this number to this number. We'll have to figure out how much is just in this little region right here, for example. We might have to do something like that. All right, so let's look at this problem. It says the distribution of the weights of newborn babies in one region is bell-shaped with a mean of 3,000 grams and a standard deviation of 500 grams. Okay, so before we even get started, I'm going to go ahead and I'm going to draw my little bell curve. And I'm going to label the mean, and I'm going to label the standard deviations. All right, so zooming in just so I can write smaller. So let's see, what they say the mean was 3,000? Yeah, I started to write 500. All right, so mean in the middle is 3,000. And then 1 standard deviation above, that would be 3,000 plus 500, so that's 3,500. 1 more standard deviation above would be 4,000. 1 more standard deviation above would be 4,500. All right, now let's label below. So if we're going below the mean, we would subtract 500, so that would be 2,500. So these are going to be like your smaller babies. Bigger babies are going to be at this end. And then we have 2,000, and then we have 1,500. So just going up and down by 500. All right, so, and also, I don't think I mentioned this, but these are called the tails of the distribution. So the ends are called the tails. All right, so we've got our little bell-shaped curve drawn. I'll let you finish it up if you're not quite finished yet. I do this every time, and I know it can be a hassle to have to draw this out every time, but I really think it helps if you draw this bell curve every time for every problem. When you're doing empirical rule. All right, so, and oh, it is also important, I just wanted to make sure it's clear that if we had not seen this part of the question where it says bell-shaped, we would not be able to use empirical rule. Empirical rule is only for bell-shaped distributions. If it's not bell-shaped, that's when we have to use the next thing, which is Chebyshev's theorem. All right, so let's look at our first problem. It says, what percentage of newborn babies weigh between 2,000 and 4,000 grams? All right, so get your pen, and I like to use a different color when I am shading in my bell curve, but here's 2,000, here's 4,000. All right, so 2,000, that's 2 standard deviations below the mean, and then 4,000 is 2 standard deviations above. And then we're looking for what percentage of babies lie between these two weights. All right, so if it's 2 standard deviations, remember the rule, 1 standard deviation within the mean, or 1 standard deviation away from the mean is 68, 2 standard deviations is 95, 3 standard deviations is 99.7. Let me look at the formula sheet. I can't remember if that's on there or not. Let's see. Some people were telling me they had already taken the quiz. That is not on the formula sheet, so this is something you probably want to put on your note card, on your little index card. All right, so since this 2,000 and 4,000, that's 2 standard deviations away from the mean, so that's going to tell us that 95% of babies, 95% of newborn babies, and I'm just writing out the full sentence here. You could just say 95%, it would be okay. Of course, on the quiz, it's going to be multiple choice, so you won't have to write any sentences. All right, so 95% of newborn babies weigh, I forgot to put that in there, weigh between, totally left out like half of the sentence there. 95% of newborn babies weigh between 2,000 and 4,000 grams. Okay. Any questions about where we got the 95 at? Does everybody feel okay with empirical rules so far? Yeah. Okay. Make sure I've got my chat up. Yes. Okay. So let's look at part B. This one's worded a little bit differently. It says, calculate the range of birth weights that would contain the middle 68% of newborn baby weights. All right, so the middle 68%, that's 1 standard deviation away from the mean. All right, so we're going to look 1 standard deviation away from the mean. Let me change my color. 1 standard deviation away from the mean, that starts here with 2,500 to 3,500. All right, so that's the middle 68%. All right, so the range of birth weights that would contain the middle 68% of newborn babies' weights would be 2,500 to 3,500 grams. All right, so 68% of babies or newborn babies would weigh between 2,500 and 3,500 grams. All right, and then the last one, this is the one that I was telling you about before we started the problem, where sometimes you have to, sometimes it's not as easy as just looking at this, 1 standard deviation is 68, 2 is 95, 3 is 99.7. So let's look at this one. It says, what percentage of newborn babies weigh less than, my goodness, I do be struggling. Weigh less than 3,500 grams. Notice that the last two problems, it was, the middle 68% or between 2,000 and 4,000. So that's why this one is a little bit different. So let me just scroll back up to my bell curve. So they said less than 3,500. So I know my bell curve is getting a little bit messy up here, but just hang with me for a second. Less than 3,500. So that's going to be here and all the way to the left because it's less than 3,500. So all of that in the pink. So all of that that's shaded in pink. All right, so let's start off and let's think about where 3,500 is. Okay, well, 3,500 is 1 standard deviation above the mean. So one way you could think about this is, okay, well, I know that from here, whoops, let me see if I can get my pen back. From here to here, I know that that's 68%, so you could build off of that. What your book does, and I think it's smart because it's going to save you a little bit of work, is you could use the fact that since this is a bell-shaped curve, you know that the mean is also the median. Remember, we learned that yesterday. The mean, median, and mode is all in the same spot for bell curves. So that means that everything to the left of this middle line everything over here is 50% of the data. Since this is symmetric, that means 50% is over here, and then the other 50% is over here. I think that's a good way to do this. It captures almost everything that we have shaded in. You can see the only part that's left over is just this little side part over here. So let's scroll down, and we're going to say, okay, well, we know that part of it is 50%. All right, so it's 50%, and then plus, we're going to have to figure out what the other part is. All right, so I'm going to draw another bell curve, since that one up there is getting a little bit messy. And then my middle value, that was the mean, was 3,000. Then I have 3,500 right here. So the only part, remember, that I had left over was from here to here. So that's how I need to figure out what percentage of data values are going to lie in that tiny interval. Now, this is 1 standard deviation above the mean, but it's only above, it's not the below. So let's think about what we know from the empirical rule. The empirical rule tells us that 68% of the data values are within 1 standard deviation above the mean. So that tells us that from here, which would be 2,500, from here, let's go the other way, maybe. From here to here is 68%. Well, this is half of that. So what is half of 68? What would half of 68 be? 34? Yes, good job, Robin. So 34% would be in this tiny little column here. So plus 34 would be 50%, plus 34% would be 84%. So that's one way that you could figure out how many babies weigh less than 3,500 grams, or excuse me, what percentage of babies weigh less than 3,500 grams using the empirical rule. And we also used what we learned yesterday about the symmetry of bell curves and how we know that the mean, median, and mode is all that middle value there. So the median is the middle value, so it splits the distribution in half. So we said, okay, well, we know that 50% is to the left of 3,000. And then we just had to add on this tiny little piece here, which we figured out by saying, okay, well, if 68% is between 2,500 and 3,500, half of that would be 34%. So like I said, sometimes the empirical rule problems are super easy, and sometimes they are a little bit more complicated, where you have to sort of use the empirical rule and split it up into pieces. Now, in case you have to do that, I wanted to draw this little picture for you to show you the percentages between each standard deviation. So I'm going to do that off to the side here, and you can just copy this down. You might want to put it on your index card. All right, so here's my bell curve. My mean is in the middle. And then I'm going to label my standard deviations. So -1 sigma, -2 sigma, and then -3 sigma. Then above I have 1 sigma, 2 sigma. Remember, sigma is the standard deviation, and 3 sigma. All right, now I'm going to draw a line for each one of these values. I'm going to try to anyway. I'm just drawing a straight line to the top of the curve. There's the mean, so I'm halfway through. And my curve obviously is not perfect. You can see I probably don't have the lines in the perfect spot to go halfway, but this is okay. All right, so I'm going to draw for you or write down the percentages that are in between each of these lines. All right, so in between the mean and the first standard deviation, 34% of the data is right there. We just figured that out. The other 34% is here. So 34% plus 34%, that's that 68 from the empirical rule. Now, from negative 2 sigma to 2 sigma is 95%. So you would say, okay, 95 minus, we've already accounted for 68%. 95 minus 68 is 27. So we know that this area plus this area is 27. So if we divide that by 2, that means that there's 13.5% right here. And then the other 13.5% is right here. So again, this is the percentage of data values that fall between the first standard deviation below the mean and the second standard deviation below the mean. All right, so that was 95%. And then we know that the third standard deviation for empirical rule is 99.7. So 99.7 minus, we've already accounted for 95%. So 99.7 minus 95 is 4.7. Divide that by 2. What did I do wrong? Did I do that right? 99.7, yes. All right, so 99.7 minus 95 is 4.7 divided by 2 is 2.35. So 2.35% right here, 2.35% right here. And then the other, this is what's left over in the tails. You get it now? Oh, good, good, good. I'm glad. Yeah, I think I drew this out for someone else in the class. Somebody was doing this like last week. They were ahead of us. And I thought this was a good way to explain it. But yeah, there is like 0.3% left over, and that's what's going to be in these tails out here. So you could do like 0.3 divided by 2. It would be 0.15%. That's so small. It's such a small amount of data values that are going to be in these very ends. 0.15. And I know my percentage symbols do not look great. But hopefully you can see what I was trying to get at here. All right, so again, you could write this on your little note card if that's helpful for you. All right, so empirical rule, you want to think bell-shaped curves. Now let's look at, I have another example here. Let me see what I wanted to show here. I wanted to show this one because I know there's a lot of people in here that are like health sciences or nursing majors. So it says, suppose the diastolic blood pressure readings of adult males have a bell-shaped distribution. Okay, bell-shaped, you want to think empirical rule, with a mean of 22 milligrams of mercury and a standard deviation of 10 milligrams of mercury. Excuse me, millimeters of mercury and 82 millimeters of mercury and 10 millimeters of mercury. Using the empirical rule, what percentage of adult males have a diastolic blood pressure that is at least 92 millimeters of mercury? Do not round your answer. All right, so I'm going to start by drawing my picture here. Mean goes in the middle for bell-shaped distribution, so that's an 82. Standard deviation of 10, so I'm going to go ahead and label 92, 102, 112. Going below the mean, 72, 62, 52. All right, so they want to know, have a diastolic blood pressure reading that is at least 92. All right, so let's draw a line at 92. And at least 92, that means 92 or higher. All right, so shade to the right. This is what we're looking for. This percentage of people out here. All right, so we are going to think about this. Oh, I think there's an easy way we can do this. Remember what we just talked about with the last problem. We said that 50% would be, let me use a different color. 50% of the data values would be from here over, right? Sorry, that yellow is so hard to see sometimes. So 50% of the data values would be from 82 to the right. But we're missing just this little piece. But we just found what that little piece was. Let me use a different color. Remember, we just found what this little piece was. Do y'all remember what percentage was in this little piece right here? What was right here? 34, yes, it was 34% was right here. All right, so we know that 50% would have been everything. So 50% minus, because we're taking away this piece, 50% minus 34% would be 50. I should be able to do this in my head. 16, that's what I thought. I really did think it was 16. All right, so that would be 16% of adult males had diastolic blood pressure readings that were at least 92 millimeters of mercury. All right, so I really like this empirical rule, and I think that the question on the quiz was kind of like this one. But don't tell anybody I told you. All right, so that's just for all of you nice people that come and listen to my sessions. All right, so whenever you see these words right here, bell-shaped distribution, you want to think empirical rule. All right, now let's talk about what do you do if you have a question like this where you're trying to figure out what percentage of adult males or whatever you're looking at have a certain value, but you don't know if it's bell-shaped or not, then you have to use what's called Chebyshev's theorem. So I think it's pretty, it looks long, but it's pronounced just like it's spelled. So Chebyshev's theorem. Now, Chebyshev's theorem looks complicated, but I'm going to show you this example, and I think you'll find that it really all it is you just, it's like a plug and chug thing. You just take the formula, plug in the number, and it's going to spit out the answer for you. All right, so Chebyshev's theorem says the proportion of data that lie within k standard deviations of the mean, k here could be 1 standard deviation of the mean, 2 standard deviations of the mean, 3 standard deviations of the mean. So typically, you're just going to be using, well, if you look in the next part of the sentence, let's keep reading. It says, the proportion of data that lie within k standard deviations of the mean is at least, that's very important that you include those words in your answer, at least, is at least 1 minus 1 over k squared for k greater than 1. All right, so you cannot use this formula for any k values that are 1 or smaller. This only works for values of k that are greater than 1. So also very important. So when k equals 2 and k equals 3, Chebyshev's theorem says the following. If you're looking at the proportion of data that lie within 2 standard deviations of the mean, that means that at least 70% lie within 2 standard deviations of the mean. If you're looking at k equals 3, that would say that at least 88.9% of the data lie within 3 standard deviations of the mean. So you can see this is a little bit more what they call conservative than the empirical rule. So the empirical rule, remember, for 2 standard deviations was 95, and for 3 it was 99.7. So this is a little bit more conservative in that it's saying that we're not sure, but we think it's at least 75% of the data are going to lie within 2 standard deviations of the mean. So you really only want to use Chebyshev's theorem if you are not sure, like I said, if you're not sure about the shape of the overall distribution that you're working with. So let's look at an example of Chebyshev's theorem. I can go ahead and tell you I don't think this is on the quiz, but there is one like this on the homework, which is why I'm covering it. So it says, suppose that prices of recently sold homes in one neighborhood have a mean of $225,000 and a standard deviation of $7,100, excuse me. Using Chebyshev's theorem, what is the minimum percentage of recently sold homes with prices between $203,700 and $246,300? Round your answer to 1 decimal place. All right, so when I was looking at this problem earlier, I thought, okay, so how would I start this? And I would start by thinking, okay, well, for Chebyshev's theorem, I need to know how many standard deviations am I working with here. So we need to figure out how many standard deviations below the mean is this value, and how many standard deviations above the mean is this value. All right, so I'm going to show you the nice and neat way to do this. So you would start off by taking your 225,000. And then let's go below the mean first, since that was the first value they gave us. So let's subtract off 7,100. So get your calculator, 225,000 minus 7,100. All right, so that would be 217,900. Okay, so that would be one standard deviation below the mean. That's one standard deviation below the mean. All right, let's go 2 standard deviations below the mean. This is the neat way to write this. You would say 2 times 7,100. If you were just doing this in your calculator, you could just do 225,000 minus 7,100 minus 7,100. So you could just subtract it twice. But here I'm subtracting 2 times 7,100. So 225,000 minus 2 times 7,100. 210,800. All right, so we're almost there. Now let's go 3 standard deviations below the mean. Oop, I left off a 0 right there. Got it back this time. All right, so if we go 3 standard deviations below the mean, that's going to give us that 203,700. So there we go. That was 3 standard deviations below the mean. So that's what we have going on here. So right now we think we're going to have to use this k equals 3. We just want to confirm and make sure that this is also 3 standard deviations above the mean. So let's scroll down here and check that. So I'm going to skip doing all this stuff, and I'm going to go straight to 3 standard deviations above the mean. So I'm going to do 225,000 plus 3 times 7,100. So let's just make sure. Yep, so that's 246,300, which is what we were looking for. So this is 3 standard deviations above the mean. All right, so now we know that the values that we're working with are 3 standard deviations above the mean and below the mean. So let's look at Chebyshev's theorem. It says that, remember, K represents your standard deviations. So if you have 3 standard deviations, if you're 3 standard deviations above and below the mean, then we know that 88.9%, excuse me, I should say at least 88.9% of homes would be between those 2 prices. All right, so let's write that little sentence here. All right, so Chebyshev's theorem said that if K equals 3, so if your standard deviations equal 3, then that's 88.9%. Once again, I forgot the at least. Put that in there. At least 88.9% of homes, they said recently sold homes, had prices between, abbreviating between there, 203,700 and 246,300. All right, so that's Chebyshev's theorem. Yeah, and we are definitely, I'm glad I made those videos this morning, because we are definitely not going to get through all of 3.3. Let's see, we talked about in section 3.2, we talked about standard deviation, we talked about variance and range, and we talked about empirical rule and Chebyshev's theorem. Make sure for the quiz, make sure you know how to use your calculator to compute the, the mean and the median and the standard deviation. And remember, you have to calculate the range and the mode by hand. All right, so the stuff that I really wanted to make sure and go through today, I wanted to talk about these formulas, when you should use these formulas. And then I'm hoping that in the next 20 minutes or so, we can get all the way down here to where I talk about box plots and the 5-number summary. All right, so measures of relative position. So what this means is it's going to tell you the position of a data value relative to the entire data set. All right, so the first formula that they have in this section, let me zoom in so you can see it. It says this is how you find a data value if you're given the percentile. So this is where, say for example, you go to, let's say that you are you have a child and you go to the doctor, and if you have a child, or if you have been a child recently, then you know that they always talk about percentiles of height and weight. So imagine that you're trying to figure out, okay, so for children that are 1 year old, what is the 25th percentile of heights? All right, so let me first tell you what percentile means. If you were trying to figure out a percentile, I'm just going to do an example here. I think it's much easier to understand if I just write out an example. Let's say that you were talking about the 75th percentile of heights. You might also see this like on your any kind of standardized test. So let's say that you score in the 75th percentile of heights. That means that 75% of people are your height or shorter. So basically, you're taller than 75% of people if you scored in the 75th percentile. All right, so that's what percentile means. It's that percentage or lower. That percentage of people are that height or shorter, or that percentage of people weigh that much or less, or that percentage of people scored this score or less. All right, so let's look at the definition or the formula. It says to locate the data value for the pth percentile. P just represents any whole number here. It's got to be a whole number between 0 and 100. The location of the data value in the data set is given by, this is an L for location. L equals N. N is the sample size, the number of data values in the sample. So location equals N times P. P is the percentile, divided by 100. It says when using this formula to find the location of your percentiles value in the data set, you have to make sure and follow these 2 rules. If the formula results in a decimal value for the location is the next larger whole number, so round up. If the formula results in a whole number, the percentile value is the arithmetic mean of the data value in that location and the data value in the next larger location. All right, so let us do an example, and it's going to be much easier to see what those 2 rules mean. Here we have a data set of weights of newborn babies. All right, so it says, given the following data, find the weight that represents the 40th percentile. Okay. So let's first look at our weights here. We have 8.5, 7.5, 9.0. And then let's see. I'm just trying to see like what's my highest value, what's my lowest. 9.5, 9.4 looks like the highest. And 5.6 looks like the lowest. That just kind of gives you an idea of like what range that you're working with there. All right, so let's write down our formula. Our formula says L, I like to do a cursive L so you can tell it's an L, not a 1, equals N times P over 100. All right, so the location equals the sample size times the percentile over 100. All right, so sample size, let's see, there's 1, 2, 3, 1, 2, 3, 4, 5. So that means there's 15 weights here. So N sample size is 15. All right, so that's 15 times P. We were looking at the 40th percentile, so it's going to be 40 over 100. Whoops. 100. So get your calculator. I got this document camera installed on my computer this morning, so you can see my calculator right here. All right, so I'm going to do 15 times. Notice how I'm just going to do this all on one line. 15 times 40 over 100. So that's 6. All right, now that's not your answer. That's the location of your answer. All right, so unfortunately, all of these need to be in order from smallest to biggest whenever we're finding the location. But it's not too bad because we don't have to really put them all the way in order. We just have to find out what the 6th one is. So this is going to be the 6th position. So again, we're going to start off by listing them from smallest to biggest. Remember, smallest, I think we said was 5.6. I'm going to cross them off as I use them. 5.6 and then 5.9. That's the second. And we have 6.0. Oops. 6.2. See, 6.4. 1, 2, 3, 4, 5. And then 6.8. And then 7.0. I think I need one more. 7.5. Okay, so let's scroll back up here to our formula and look at those rules again. If the formula results in a decimal value for L, the location is the next larger whole number. Okay, we got a whole number, so let's look at the next rule. If the formula results in a whole number value for L, that's what we got. The percentiles value is the arithmetic mean of the data value in that location and the data value in the next larger location. Okay, so this was first, second, third, fourth, fifth, sixth, seventh. Okay, so we need to find the mean of these two values right here. So this was the 6th position. This was the 7th. So let's go down here, 6.8 plus 7.0 divided by 2. That's how you find the arithmetic mean. So I'm over here on my calculator. I'm doing 6.8 plus 7.0 divided by 2 is 6.9. So that is the location or the weight that represents the 40th percentile. So 6.9, and I think this is pounds. There we go. So that is the 40th percentile. So when should you use this formula? You should use this formula if you're asked a question like, find the 40th percentile, or find the 50th percentile, or find the 12th percentile. So if you're asked to find a percentile, this is the formula you use. Now the next formula, it's going to sound, the description sounds very similar, but it's actually the opposite. So on this one, you're not given the percentile. So you're trying to find the percentile of a given data value. So on this one, your answer is always a number. On these, your answer is a percentile. All right, so it says finding the percentile of a given data value. The pth percentile of a particular value in a data set is given by the percentile equals the location over the sample size times 100. All right, so location over sample size times 100. Now, I have this example here of a stem and leaf plot because I wanted to show you how you would take a stem and leaf plot and deconstruct it. I think I'm only going to do one of these examples because we're already at 12:49. I'll keep talking. If you have to go, that's fine, and then you can just watch this recording later, the rest of it, because I do want to make sure and get through all of this today. So it says the following stem and leaf plot represents the time in minutes required for 30 co-workers to commute to work. So remember, stem and leaf plots, the way these work is this would be like 20 minutes, then 22 minutes, 22 minutes, 25 minutes, 25 minutes, 28 minutes. Okay, so let's look at the question. It says, find the percentile of the commute time, 46 minutes. Right, so 46 minutes. It's right here. 46. Right there. All right, so let's look at our formula. P equals location divided by sample size times 100. Okay, so, oh my goodness gracious. All right, try again. Percentile equals location divided by sample size. Let me make that a cursive L times 100. All right, so let's see how they define location. L is the number of values in the data set less than or equal to the given value. Okay, so the number of data values that are less than or equal to 46. All right, so we're going to start counting here at 46. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right, so there are 17 values less than or equal to 46. Let's see what the total sample size is. They told us it was 30. So 30 times 100. All right, so let's take your calculator over here. 17 divided by 30 times 100. You can do this all in one line. Notice that I didn't have to put anything in parentheses here. Once you type the 30, your calculator knows, okay, she's done in that fraction since she typed the multiply sign. All right, so 56.67. Let's see what they want us to round to. It says P is the percentile rounded to the nearest whole number. So this would be the 57th percentile. Right, so this would be the 57th percentile. All right, so again, if you're asked to find the percentile, you're going to use this formula, location over sample size times 100. If you're asked to find the location of the data value, or to find the actual data value, you're going to use that formula before the location equals n times the percentile over 100. All right, so just make sure you're being careful and thinking about which formula should I use here. What are they asking me for? Now, I thought originally I wasn't going to go through this just a few minutes ago, but the more I think about it, I think I do want to go through this. Because if we look, it says find the percentile of the commute time, 57 minutes. Notice that we have one, here's 50, here's the stem 5. So 57 occurs 3 times. So I did want to show you what happens when you have a data value that occurs more than once. All right, so this is, we're looking for a percentile. So again, we know that we're going to be using our percentile formula. P equals the location over n sample size times 100. All right, so let's start here. 57, remember location is the number of data values that are less than or equal to that number. So 57 starts right here, or actually ends right here. So let's start counting back from here. Let me erase my little line under 46. Okay. So 1, 2, 3. Do I really need to count these? How many are in this data set? Didn't we know that 30 were in the data set? So since this is everything, if I started here and was counting to the left, I really don't need to count everything. I already know that there's 30, right? Yeah, so right, Rebecca, there would actually just be 30. So my location is going to be 30. So that just saved us a little bit of time. sample size was also 30 times 100. 30 over 30 is 1. 1 times 100, this is the 100th percentile. So the highest value is the 100th percentile. The lowest value would be the 0th percentile. All right, so if they're asked for the highest percentile, that's really no work for you to do. You know that if it's the highest value, 100% of the data values must be below that number. Must be, that number or below. So that would be the 100th percentile. All right, now we need to talk about quartiles. Quartiles are just special percentiles. These are just special percentiles. So they're basically just percentiles that have special names. All right, so quartiles. Quartiles are values that divide an ordered set of data. Notice it's very important that the data are in order here. Quartiles are values that divide an ordered array of data into 4 equal parts, equivalent to the 25th, 50th, and 75th percentiles. Now let me zoom in so you can see these special symbols. Q1 is the first quartile, or the 25th percentile. Q2 is the second quartile, or the 50th percentile. All these things mean the same thing. So Q1 is the same as the first quartile, which is the same as the 25th percentile. Q2 is the same as the second quartile, which is the same as the 50th percentile. And Q3 is the third quartile, which is the same as the 75th percentile. All right, so the second quartile is also known as the median. 50th percentile, or the second quartile, is also known as the median. Now, the nice thing about when you're asked to find a quartile, these are going to be really easy because your calculator can tell you quartiles using the same steps that we learned yesterday. So again, we're working with the stem and leaf plot of commute times for work. So get out your calculator and let's type this data set into our calculator. All right, so go to Stat and let's edit our list. So select the first option, Edit. Now I've got a set of data in here already, so I need to go to the very top and I'm going to hit Clear. So the Clear button right here, and then I'm going to hit Enter. And there we go. The list is cleared out. And remember what I told y'all yesterday. Make sure that these say L1, L2, L3, and so on. So make sure you're not missing one of your list. All right, so we're going to start typing in our data. If you look over here at our stem and leaf plot, it starts off with 20. So 20, and then 22, 22 again, 25, 25 again, and then 28. All right, so now we're on to the next stem of 3. 33, 34, 2 times, 35, 36, 37, 38, and 39. And then down to the stem of 4, we have 42, 44, 46, 47 twice, 48 twice, and then 49. Then in the stem of 5, we have 52, 53 twice, 54, 56, and then 57 3 times. Now, like I mentioned yesterday, it's a good idea to go back through your list and just make sure you didn't miss anything. So just scroll back through your list, make sure everything's there. I'm pretty sure I did this right. All right, so once I'm going to give you a minute to finish typing everything in your calculator. And then we're going to do just like we did yesterday, where you go to Stat and then over to Calc and then 1var Stats. Okay. Hopefully you've got all your data in there by now. Somebody message me? No? Okay. All right, so go back to Stat and then go over to Calculate. Remember, Calc stands for Calculate. And then we're going to select our first option, one variable stats. Hit enter. Mine comes up with this extra screen where it asks me which list I'm using. I'm using L1. All right, so I'm going to scroll down, hit calculate. And there we go. Sorry about that. You can see it's got my mean up here. My mean is 41.27. It's got my standard deviations. It's got my sample size. And scroll on down a little bit. And there we go. You see that Q1, median, Q3. Oh, man, isn't that easy? Makes this so much easier than having to use those formulas and having to count up stuff. All right, so second quartile. Remember we said another name for the second quartile. They called it Q2, but you could also call it the median. So the median is, if you look over here, 43. So 43. You can see it's actually not one of our values of our data set. So you must have had to, you know, do the arithmetic mean of two of these. Okay. And then it says, part B says find the first quartile. And look, there it is, Q1. Q1 is the first quartile and it's 34. Doesn't that make that so much easier? 34. All right. Anybody have any questions about finding the quartiles? So you can see there's the third quartile, 75th percentile is 52. There's the second quartile and the first quartile. So this one variable stats tells you a ton of useful information. All right, now while we have this screen up, I want to talk about the 5-number summary. The 5-number summary is going to be given, it's the last 5 numbers on your 1var stats. All right, so this is the data set we just typed in. And look at our last 5 numbers. Here's the first, second, third, fourth, fifth. So those last 5 numbers from here to here, that's our 5-number summary. All right, so a 5-number summary is the following. It's the minimum, the first quartile, the median, also known as the second quartile, the third quartile, and the maximum. So that's your 5-number summary. A 5-number summary is a great sort of compact way of describing an entire data set using only 5 numbers. It tells you the smallest value that's in the data set. It tells you the 25th percentile. It tells you the halfway point, the median. It tells you the 75th percentile, and then it tells you the maximum. All right, so it says write a 5-number summary for our data set here of commute times. So we're just going to copy down our values from right here. And on the homework, what they have you do is write these separated with a comma. So that would be 20, comma, 34, 43, 52, and 57. I forgot to ask this before, and I'm sorry, I totally meant to ask this, but did anyone else get different numbers? If you got a different number here, then you may have typed something in wrong. Did everybody get these numbers? everyone is like asleep. Oh, we still have a few people in here. All right, so let's look at what we use the 5-number summary for. The 5-number summary, thank you all for staying late. I appreciate it. The 5-number summary is used to create what's called a box plot. Box plots are a different type of graphical representation of a data set, and they are used specifically just for quantitative data sets. All right, so box plots are graphical representations of a 5-number summary. All right, so I wanted to zoom in and show you. This is what a box plot looks like in general. Some books will call them box and whisker plots because these lines on the end are referred to as whiskers. But the way that this is set up, let me draw what each of these little spots means. All right, so this spot down here, that's where your minimum value goes. Okay, so at the very end of that whisker is your minimum value. This line here is your first quartile. The middle line is your median, also known as the second quartile. This third line, the end of the box, is the third quartile. And then at the very end down here, we have the maximum value. All right, so goes your minimum, and again, this is your 5-number summary. The minimum, the first quartile, the median, the third quartile, and then the maximum. And you can see I've got the lines drawn different lengths here. The longer side is not always necessarily on the left. This is just the way I drew this box plot. Sometimes the line may be longer on the right. It depends on how skewed the data is. So here it looks like there are more outliers on the left. So I think that would make it be skewed right for this data set. So the longer the line, the more skewed that data set is. All right, so the next thing I wanted to show you is these are the steps for creating a box plot. You can also create one on your calculator. If you go to second y equals, that takes you to the stat plot list. If you click on that first one, if you see right there, there's a box plot right there. So you can create one with your calculator. In this class, I won't ask you to draw any box plots. I'll just ask you to interpret box plots. But if you ever wanted to use your own data set, so I was talking to Dr. Holbrook the other day from biology, and he was telling me that if you are a biology major and you take some of their upper level classes, you may have to do some statistics. And so you might have to create a box plot for your data set in a class like that, or in psychology or in nursing. So if you needed to create a box plot, these are the steps. And again, you can do it on your calculator. You can also do it in a program like Excel. Speaking of Excel, someone was asking me this morning, could you use Excel on the quiz? And if we were, face to face, I would be fine with you using Excel. But since we have to use the lockdown browser, it won't allow you to open Excel during the quiz. So that's why I don't have it set to where you can use Excel on the quiz. So on the left-hand side here, I think we can go full screen for this one. It says, a high school has 28 players on a football team. The summary of the players' weights is given in the box plot. All right, so here's the box plot. See, it's got a number line underneath it. Typically, that's how they're drawn. So it has our minimum is 160, first quartile is 172, median is 222, third quartile or 75th percentile is 243, and then the maximum weight is 256. All right, so again, what is the median weight of the players? That would be this line right here, so 222. So these questions are all about just reading box plots. So super easy. As long as you can remember what the 5-number summary is, you'll be able to get these pretty easy. All right, and then I wanted to go over this one, whoops, where you're comparing two data sets. All right, so here it says, consider the following box plots for data set A and data set B. All right, so here's our first data set A. You can see has minimum of 54, first quartile 64, median is 71.5, third quartile is 83, and then the max value is 94. And then we have 48, 54, 74.5, 81, and 87. All right, which data set has the largest value? All right, so y'all tell me, what do you think, A or B? I know it's hard to go in between the chat and watching the video, so you can just unmute yourself if you want to.
B.
The largest value, I think, would be in A, because it's got this line out here to 94. So that would be the larger, the one that has the larger data value. All right, so data set A has the larger value. Data set B has the smallest value. Notice it has this line that goes out to 48. This one only goes to 54. So data set B has the smallest value. All right, and I'm going to scoot my picture down. And this question, I like this question because it kind of ties in something that we learned back in section 3.2. It says, which data set has the largest variation? Remember, we learned that variation means the same thing as dispersion. And so the way that I thought would be a good way to determine this would be to look at the range. All right, so which one has the largest range? Remember, range is maximum minus minimum. All right, so the range for this one would be 94 minus 54. So that's 40. Now we got to see, does data set B have a range that's larger or smaller than that? So it's 87 minus 48. So let's see, that would be, nope, can't do it in my head. 87 minus 48, 39. All right, so the one with the larger variation would be the one with the larger range, so that would be this one. All right, so data set with the largest variation would be data set A. Does that make sense? Is that okay?
Yes.
Okay, good. Thank you. All right, and that is it for today. From here on out, that's where I made the videos this morning. All right, so we talked about a lot of stuff today. We talked about the empirical rule. We talked about Chebyshev's theorem. And then we talked about those two formulas. Oh, shoot, I forgot to tell you this part. My bad. Let me go back and talk about this really quick. When we were talking about the 5-number summary, I forgot to tell you about the interquartile range. The interquartile range tells you the distance from, sorry about that, you guys. It tells you this distance right here. So it's called the IQR because interquartile range is really long, and it has a little formula. It's really easy, and I actually have this formula on the formula sheet. So the interquartile range is equal to Q3, so the 75th percentile, minus Q1, which is the 25th percentile. All right, and the reason that I wanted to introduce the interquartile range to you is because I talk about it in this video that I made for identifying outliers. So I wanted to have mentioned that to you in this video, that the interquartile range is calculated using two of our numbers from our 5-number summary. So it's IQR, interquartile range, equals Q3 minus Q1. All right. So again, we talked about box plots. We talked about the 5-number summary, quartiles, percentiles. We said that quartiles are just special percentiles that have special names. We talked about how you can find the percentile of a given data value, like find the percentile of the commute time 46 minutes. Or you can do sort of the opposite of that, which is to find the data value that corresponds to a particular percentile. All right, so these two formulas are on your formula sheet, but you may want to write something down on your index card to help you remember when to use which formula. All right, so that was a lot of talking. I feel like every day when I leave here, I have like a sore throat because I never talk this much. But hopefully that was helpful, and hopefully you will have time to go watch those other two videos. I think one of them is like 12 minutes and one is 9 minutes. So you can watch those later at your convenience. And if you remember, I told you if you go to content and then unit 2, they're down, I think it's like second box from the bottom, and it says additional resources. And I've linked both those there. And like I said at the beginning of class, if you're interested in joining the study group, you can find the details on how to do that in the announcements on our course homepage. All right, so hopefully you guys feel comfortable with Chapter 2 and Chapter 3. If you do have any questions before you take the quiz, please feel free to email me. I just finished writing the answer key, so I'm about to go upload that, and I'm going to try to set it to release it whenever you submit something to the Dropbox. So hopefully it'll release itself. But I'll post an announcement whenever I get the answer key up. But I hope you all have a great weekend, and I will see you on Monday, and we'll be talking about Chapter 4, which is probability, I think. All right. See you guys later. Bye.